So, Ilaria, maybe tell me a little bit about how you got into your field you study.
So I started. So when I was in the secondary school, basically I decided that I wanted to do astronomy, and it was because I was interested in learning about the universe.
And where did you grow up? People will hear your accent. So.
Yeah, I'm Italian, so I grew up in Italy in a small town, just 50,000 people.
Wow.
And then, as I said already, when I was in the secondary school, that's what I wanted to do. So then I went to the university in Bologna. That's where I studied, and I.
Which most people don't know, but it's a very old university, right?
Yeah, actually, we like to say that it's the oldest university in Europe. But then I did a PhD in Heidelberg, where they told me that is the oldest university.
Oh,
so that was kind of funny.
Little argument. Okay.
Yeah. So then, yes, I did further studies in Germany. And after that, after having a PhD in astrophysics, I moved to the US as a postdoc, and since 2004, that's where I am.
And you're a theorist primarily, right?
Yeah, I do theory and as well as observation, so I like to combine the two.
Okay. So I want to talk about planet formation, and I just to start in very general terms, I think for many people it's amazing that you start with this cloud of gas and dust, and it's diffuse and has very little structure, and then you end up with a star and these planets in their very particular orbits. I mean, can you just paint a general picture of how we think this happens?
Okay. So
just the sort of high-level view, if you like.
Okay. So yeah, as you mentioned, basically, we think that it all started with a cloud of gas that was basically accreted mostly onto the central star, and because of the rotation of this cloud, then the round cloud that we have first in mind started to flatten into more a pancake-like shape, more a disk. That's how we call it. And then with time, these initially very tiny grains that are submicron in size, meaning you cannot even see them with your eyes, they started to stick together and then grow into larger bodies.
And initially they're not even sticking by gravity, right?
Yeah, that's right. This Brownian motion, and I don't know, it's too difficult.
Yeah.
And but then once they grow enough, like they are kilometer in size, then gravity starts to matter at that point. And there is, we think there is a threshold in mass of these large bodies above which then they start to accrete also the gas from the disk, so they can form the gaseous envelopes of giant planets like Jupiter and Saturn. So the one interesting thing in the theory and also in how the solar system look like is the distinction between the inner planets and the outer planets. The inner planets are mainly made of rocks, and the outer planets are much larger, and they have also a large envelope of gas. And we basically understand how that distinction happens, and is due to the condensation of water vapor into ice beyond a certain radial distance from the star, which we call the snow line.
And where in our solar system is the snow line?
Yeah, it's roughly at the location where the asteroid belt is a bit in the asteroid belt is today. So we understand that the inner planets, Mars, Venus, Earth, and Mercury, they accreted, we say dry, because the rocks from which they formed didn't have any water ice into them, while the outer planets, they accreted, we say wet, because the rocks from where they formed, they had water ice into them.
And of course you have to rewind the clock, because the sun wasn't the same luminosity when the solar system formed as it is now. So how does that affect the situation?
That's perfectly right. So there is a lot of, there are many theoretical studies in trying to understand exactly where this snow line is changing with time. And we think that it has changed exactly because the sun was also, its luminosity was changing with time. So it has been moving around, and the details are a bit complicated. But the thing we understand is very well is why the outer planets are larger than the inner planets.
Right.
Basically, because they formed beyond the snow line, the surface density of the disk was larger, meaning there was more material to start with, and therefore the cores of the giant planets, they accreted much faster than all the other cores inside. So they could then get also gas from the solar nebula.
Now we talk about the cores, but of course we look at the giant planets we don't see. How certain is it that they have rocky cores?
Yeah, that's also true. So we think there is some, I mean, especially for Saturn, there is more evidence that it has a core. These are not, well, we don't know the exact details. They could be a few times the mass of Earth, or perhaps up to 10 times the mass of Earth. It's a very difficult measurement, but we do think that they have a core that is made of, or was made from the accreted rocks of mixed with ice, basically. And there is some indirect evidence that giant planets would have some cores through the studies of exoplanets, basically.
Right.
Because we do see that the amount of, we call them metals, basically, the amount of elements that have an atomic number larger than hydrogen, we say that, is correlated with the number of giant planets.
Okay.
We suggesting that the more heavy elements you have, the easier you can form the cores of these giant planets.
Now, another interesting thing about this formation is it's pretty rapid. I mean, in terms of astronomical timescales, to go from the initial cloud to fully fledged planetesimals and planets. How long does it take? Do we know?
Yeah, so we have some indirect evidence. We, for instance, know that gas and dust are present around young stars for at most, say, 10 million years, these protoplanetary disks. And when we look at many objects in different star-forming regions that have different ages, we can have some also statistical numbers for the average time that a disk is around a typical star. And that time is only 3 million years.
Wow.
So by 3 million years, we think that at least the giant planet should have formed around the sun. Yeah.
So you also are talking about an important part of this whole subject, where when you have these processes that take place over millions of years and you can't watch them happen, you have to find examples at different evolutionary stages elsewhere. And is that successful? Can we find all the different stages of this process?
Well, that's of course very difficult, but the universe is large and we have many examples of regions that are tracing different time scales. So that's what astronomers do. They look, for instance, at a very young region like Orion, where there are stars that are only 1 million years old, and then we can study the properties of the dust and gas around these young stars. And then we look at some other intermediate regions that are 5 million years old, and then in some other old ones. So yeah, we have, I think now, at least for the component studying the dust around these young stars, we have a very good sampling going from 1 to 10 million years.
And so back to the solar system for a minute, people who look at the behavior, it's very regular, all the properties seem very smooth and continuous, but then there are these oddballs, there's Venus, which is upside down, and Uranus is on its side, and when you see these peculiarities, do we know how to explain them? Or, I mean, it's hard, no one was there to see what happened, so can we explain the exceptions to the rules?
Yeah, so that's a very important question, because the short answer is we have some ideas on how to do that, and but of course we are not sure that is the right one. So that's why it's always important to confront our theory with the observations that we have. But for instance, in terms of odd examples like hot Jupiters, so these are giant planets that probably formed beyond the snow line, and now we see them very close to the central star. what we think has happened is that at some point during their formation and evolution, they have started to migrate inward through the interaction between probably other planets, but mainly because of the gas that it was orbiting around the star. So we understand that in terms of migration. Other example, like you were mentioning Uranus, we think there were probably interactions between at later stages, gravitational interaction between this planet and other planets nearby that could have changed somewhat their orbit or their tilt. So that's how we think about it.
And of course, people think of the solar system as regular and it doesn't really change over large time scales, but I mean, not all. I mean, our planet system, that's a simple question, I guess. Is it stable? Is it going to look the same billions of years from now as it does now, our solar system?
Not quite, because it was also the sun that is actually changing. Its luminosity is changing. So one thing that actually is quite interesting for us, I think, is that the location that we call the habitable zone, where the liquid water can be present on a planet, is changing with time. And we know that in 1 billion years or so, basically Earth will be out of more or less of that region.
So we better have a plan.
Yeah, we have time for that, yeah.
So habitable zones move. That's of course interesting.
The other thing I think it's interesting, I mean, we have seen it also recently with the meteor impact in Russia. There are always smaller bodies that could be from the asteroid belt or sometimes even from the comets, so from the Oort cloud region, that can move closer into Earth, so the solar system is actually not static as we might think of while we are living here. So there are things happening meanwhile.
Does that even extend to the major architecture? I mean, are the 8 major planets, are they going to stay in their current orbits for as far as you can project into the future, or are they maybe unstable at some point?
I think it's possible that they will become unstable, though I didn't think about this question, but I certainly know that they were unstable in the past because we have evidence, there are strong suggestions from models that actually we started from a more compact configuration and then the planets, they moved outward. So
independent of the changing luminosity of the sun, the planets can move around and be in and out of habitable zones by migration, by their own movement.
Yes, but probably not for the solar system right now.
Right.
I mean,
right. So does most of the large scale movement happen early, or can it happen at any time in the evolution?
So the migration, definitely the one we were talking for, the hot Jupiters, definitely has to happen early because it's linked to the presence of the gas, basically. And then later on, migration between the planets or gravitational interaction, they can happen if the planets are close enough that they can perturb their orbits. But if they are separated enough, then they are likely going to be stable for a long time. So we shouldn't expect much of a move.
So, talk about the general changes to the subject, especially the theory when we discovered exoplanets. So when we only had one solar system to explain, there's always a worry that you're telling a just so story, that you explain the thing you know the best and what you understand doesn't apply elsewhere. So we got obviously some big surprises with exoplanets. How did that affect the theory of how planets form, to find the first other examples?
Yeah, well, definitely one thing we have learned from exoplanet is, one aspect we touched upon before, is that the formation of the planets is not as smooth as we might have thought when we were studying only the solar system.
Right.
So especially early on in the formation of the planets, there is a lot of interaction between these planetesimals, and there can be migration of the giant planets as well. So we have definitely learned that the formation of the solar system or planetary systems is a much more dynamic process than we thought initially.
And just to explain that one issue, the first exoplanets found a lot were hot Jupiters. How is it that we know they couldn't just have been formed there? When we saw those things orbiting close and very hot, how do we know they didn't form there?
Well, that's a very good question. The issue is that there was not enough mass, basically, to form those big planets at that location. So they must have formed outside and of the snow line and then migrating inward, basically outside a few astronomical units and then migrating inward.
And why do they not just go fall all the way in? There's a strong gravity of that star, so why do they park?
Yeah, so that is actually not well understood. One simple explanation is that probably the protoplanetary material was truncated at some radius. So in other words, the gas and dust, they were not continuously close to the central star, but there was a truncation radius, so they stopped and they parked there. But that's actually not enough to explain all the properties of the hot Jupiter, so there must have been some other interaction between them, the star, and possibly other planets that were there. And yes, we also think now that some giant planets might have formed early on. They migrated inward, and perhaps some of them they ended up onto the star.
Okay.
So it's also possible that we lost some giant planets.
Another thing I remember from the first 100 or so exoplanets is they had high orbital eccentricities. They were more than the eccentricities in the solar system, outer solar system. And is that still generally true, and is it understood?
Yeah, that is, well, at least from the radial velocity we get these measurements, and yes, there are still many planets that are in eccentric orbits, and the only way to explain that is again through interactions between the planets once they are fully formed, because if they would form only in a disk of gas and dust, the interaction between the planet and the gas would help to somewhat circularize, so make the orbit more circular than elliptical. So that's how we understand. But another thing that we learned from the giant planets that I'm very interested in for the theory of planet formation and evolution is that there are pileups of giant planets at specific location from the central star, like for instance at 1 astronomical unit. And the way and actually this was one of my ideas, we understand this is through another process that can disperse the gas and dust in protoplanetary disks. And this is through carving of gaps at specific location from the central star because of the way the star heat the gas. So the gas is leaving the system at specific location and then creates gaps. And the giant planets, when they try to migrate inward, they get stranded at those gaps, so they cannot fall in. And it appears like 1 astronomical unit is a preferential location because of the specifics of how this method
And this
works.
is not strictly a resonance phenomenon then,
No.
It's something different. It's gas dynamic. Yeah.
Yes, and it's related to the process of so-called photoevaporation, which is a similar process that we see in disks in Orion, when there is a massive star that is eating the gas and that gas leaves the system in a kind of a wind. In the case of many other systems, what happens is that it's the star, the central star, that is providing energy to lift the material from the surface and carve gaps at specific locations. So that's...
And maybe this is related to the eccentricity or not, but I read, in the last few years of systems found where the inclination of the planet orbits is also quite unusually extreme, because most of the planets in the solar system are coplanar. Is that a general phenomenon, or is that just a few systems that have this?
I think that it is not so general, and actually it's a very difficult measurements to do, so we do not know. But I think the norm is that the planets are in the same orbital plane, and then there are, of course, some exceptions. And I think those exceptions may be due in some cases to the interaction between the star, a companion star, and the planet. So there you need a more massive body to perturb the orbit of the planet around the primary star.
Right.
So it's again more dynamical interaction that we see in these systems.
So now that we have hundreds of, thousands of exoplanets and also a large number of multiple planet systems, I don't even remember the number. How many multiple planet systems? There's like 100 or more?
Actually, I think there are more than that now, because it was of several hundred,
Okay.
I think, now.
So now we have these good statistics. Are we in a position to say what the full range of exoplanet properties are, or to say whether our solar system turns out to be a little unusual or not? Is the Copernican principle wrong?
Well, that's a good point. I mean, that's something that I would actually like to do, and I'm trying to work on that, to connect the basically early stages of disk evolution and planet formation to the exoplanet population, and then see whether we can say something about typical properties, so removing the observational biases. And I think we are not there yet, so but that's certainly a research line that is very interesting and should be done.
Right. And now, of course, we're finding Earths, and I know one of your research interests is what NASA likes to do, follow the water. So, people, they are excited by Earth-like planets, of course, but they also want to know if they're habitable, and they want to know if they could have oceans and be Earth-like. What do we know so far about that kind of thing, about the habitability as far as where water goes in a solar system?
Yeah, that's an important question, and it's a difficult one to answer, because if we look at the models of terrestrial planet formation, what we were discussing before, we would expect the terrestrial planets, including Earth, of course, to accrete from dry rocks. So basically, we wouldn't expect to have water in these planets to start with. So the most accepted idea is that water was brought somewhat later in the game, perhaps by impacts of asteroids that formed outside the snow line, or perhaps even by comets, which are also large bodies that's formed well beyond either the location close to Jupiter or in the Oort cloud. So I think this is the favorite view. Another view, which I think, however, is perhaps even more interesting one, is that you might somewhat, we say, absorb water into grains, meaning you can trap some water molecules that are in the gas phase into dust grains, and perhaps preserve that water even when you do the build-up of the planets, and then release the water through the volcanoes later on. So I actually am very interested in this one, because it would imply that all the planets, even those that form inside the snow line, they could have some water. And we have actually some evidence that there was past water on Mars, which I think it's a good argument to support this idea, as well as we know there was water on Venus because of the hydrogen to deuterium ratio that we see in the atmosphere. So Venus had water and then it lost it. So at least the solar system, I think, is suggesting that perhaps this other idea that water can be absorbed onto dust grain is a plausible one.
And of course, one place where we have to test these ideas is the Earth. So can we use the Earth as the example to test these two ideas? Where does the Earth get its oceans from?
Yeah, I think a very interesting study is the one of minerals, very old minerals that are called zircons. So what geologists have found is that the properties of these zircons suggest that the oceans were were present very early on, and the temperatures were very mild, just 100 million years after the formation of Earth.
Wow.
So this would suggest that actually the oceans formed basically very early on. So whatever process should have helped the formation of the ocean in very early.
That's amazing, because 100 million years, you imagine the surface is only just solidified. I mean, the moon formed, 50 million years after formation? So.
Yeah, that number is changing from time to time, but yes, about that time.
But the impact rates were crazy back then, right?
Yeah, that's right. So after the cooling, basically, of Earth, almost immediately there was an ocean.
So is that enough to actually say, that's interesting, because I think the oldest the oldest solid evidence for life on Earth is like 3.7 billion years, and then people speculate about 4 billion. But can we say that the Earth was habitable 4.4 billion years ago? Is it possible?
4.4. Well, possible, perhaps with some extremophiles.
Yeah.
I don't know.
So we know those.
But actually, there are the same group who was studying the zircons is pushing forward another technique. Basically to look at isotopes of carbon 13 over carbon 12 in very old rocks that are 4 billion years old, and I think they are in Greenland. And they see evidence of an enrichment of carbon 12 over carbon 13, which would suggest that there were some organisms there doing metabolism and taking more of the carbon 12. So that's an indirect evidence, of course, but it's an interesting one, I think.
And I guess the number of major impacts was still large enough that I suppose it's possible life could have started on the Earth and then been sterilized, or it could have been multiple stars to life, right? If the impacts were still happening, the big ones.
During this heavy bombardment of
which was
of
when
the
that's 3.9, 3.8
yeah,
or something.
something like that. Although there are new studies that actually suggest that even there were this large impact, basically most of the heat was on the surface of Earth. So if you would have had life beneath the surface, and especially some extreme organisms like thermophiles, those that are hot like organisms, then they could have survived. So it's possible that these impacts were not as sterilizing and as we might have thought initially.
So the exoplanet field is moving so fast. When it's good because you do the theory too. So which of the observations in the last few years are most excite your interest as a theorist? I mean, because there's so many now. No longer you get a newspaper headline for finding a planet. They release 100 at a time. But what is the most exciting thing to you in the last couple of years?
For me, the most interesting things are these super Earth. Because we have found many of them. We do not have them in our solar system.
Right. And define what is super Earth?
Basically, they are objects that are, say, 2 times the mass of Earth, something like that. We do not really know what is their composition, though we can get now some ideas about their bulk density if we can observe them with 2 different techniques, like radial velocity, where we get a mass, and transit, where we get a radius. Then we can have an idea about the bulk density. But they are interesting because one of the possibilities is that they could be like ocean worlds, so that they would have a lot of water on their surface, which is of course interesting for habitability. And the other thing which is interesting is that they are so numerous, they seem to be a norm basically around other stars, and they seem to have formed in situ, so which would be also easier to model in the near future rather than having all these dynamical interactions with other planets.
Right.
So I think those are very interesting objects.
And what about the question I tagged on a few minutes ago, just how in the understanding we don't understand the full range of properties, how abnormal is our solar system? Is it typical? Are we finding solar system analogs or close to them?
So far, not. There are a few cases of scaled down solar system around, for instance, lower mass stars. We have a few of them, but we have to understand that our techniques are not developed yet to find a true solar analog. So if we look at the diversity out there, our solar system doesn't look common at all, but we need to understand that there are still some biases that we have to work on. So I think in the next few years we should be able to know what is the frequency of Earth-sized planets around 1 astronomical unit. Basically, we will see how common is Earth around other stars. And then the exact location of the other planets we will have to see if they match with our solar system.
Now, I remember being surprised when I started reading about M dwarfs and people looking for planets around stars that were not exactly like the sun, and realizing that the habitable real estate could be as much because there's so many of those stars. So, but in general terms, I mean, talk about the range of stars. Do we expect to find planetary systems around all stars up and down the mass spectrum, or are there sort of limits expected theoretically?
One limit would be, of course, how much mass you have available to form the planets. So one thing I study is how the disk mass, so the mass in gas and dust around young stars, changes with the mass of the central star. And one thing we could measure is that the ratio between the mass of the star and the mass of the disk is about constant, which implies that as you move down to very low mass stars and even brown dwarfs, the disk mass is going to decrease proportionally. So I think we can say fairly accurately that we do not expect to have giant planets around brown dwarfs if they formed in a disk.
But terrestrial planets?
But terrestrial planets, yes.
Yeah.
I think we can go down to the brown dwarfs. So it's quite, there should be many.
Right.
And we know that there are already.
And of course, we already know in terms of what habitable really means for biology that, the stellar radiation directly, it needs an energy source, right? So you could have geothermal energy or other energy sources, right? So habitability is a slightly flexible concept. Yeah. So where do you think will be, I mean, the rapid change in the observation is amazing. It's very hard to predict, but what else on the horizon, what do you think are the most interesting things that are going to happen in, say, exoplanet work in the next decade?
Well, I think what will be, first of all, I'm looking forward to know what is the number of Earth-sized planets.
Which is Kepler's goal, and
it
will deliver. It will deliver.
We will know it in a couple of years, I'm sure. We will have that number. And then I think what is more interesting will be the characterization of, in general, of the exoplanets, so looking at their properties, but of the atmosphere and their composition, but most of all, I think of the Earth-sized planets, because via indirect ways we would have the capabilities of detecting some biosignatures, and that is, I think, is the most exciting thing.
And I think people seduced by the rapid rate of progress in this field might not realize that how hard that is. I mean, finding Earths you can do, and it's hard, but characterization is another big step, right? Yeah,
definitely, and it's clear that unfortunately the Kepler is a machine that was built for statistical purposes. So most of the planets that Kepler is detecting are very far away from us, and we have basically no chance to follow up on understanding their characteristics. So there is an intermediate step in between knowing the number of Earth-sized planets around solar-type stars and characterizing them, because we have to understand well our neighborhood and find those Earth-sized planets that are close to us that we can then characterize.
So there's presumably complementary projects underway now to look more at the solar neighborhood, right?
Yeah, definitely with the LBT. There is a large project going on now, which is first characterizing the amount of remaining dust that we have around nearby stars, because that remaining dust can actually be a problem for detecting Earth-sized planets around nearby stars. So that's the first level. And then once we have sorted out the systems that are potentially interesting, I'm afraid then we will need a mission to characterize them, to characterize their atmosphere.
So space, we need the space environment for doing some of this work.
Which we don't have at the moment. I mean, there are some ideas out there.
And of course, NASA's budgets are not putting some of these missions right in front of us. So you think it may take a decade to do biomarker work, or?
Yes, I think the biomarkers, yes. At least on truly Earth analogs. Then if we would want to try some scaled-down version of Earth analogs, for instance, around M-dwarfs stars, then I think we could do something with JWST. So in perhaps 5 years.
Yeah. No,
So
still.
half a decade.
Okay, not too long to wait for something that exciting. Okay, well, thanks very much, Ilaria.
Well, thanks to you.